officially to order. We've got our usual gang on Zoom, so everything's up and running. Hello. And we'll kick things off with our introductions. I am Diane Hall, president of the WASP for this year, and over to you in front.
Bob W., President Emeritus.
Shaky me. Doesn't work. All right.
Do we have any new faces tonight? Two new, brand new people. Welcome. What brings you here? How would you find out about us?
Well, I'm James. I'm really into astrophysics and astronomy, and what brought me here is I really like to take pictures of the moon.
Awesome. That's great.
This is really cool. It's awesome restaurant. And another visitor is, I say that it's a case in astrophotography is really sort of starting out. So it's kind of a lot of things to talk about astrophotography.
Very good. We have some excellent astrophotographers in the club. Okay. First time attendees. So do you know about our other events? We have on Mondays, the first Monday of the month, we meet at Cranbrook Institute of Science. On the fourth Saturday of the month, we have our free open houses up at Wolcott Mill Metro Park in Camp Rotary. So that's when we have our observing nights. All right. Officer reports. Residential business-wise, we have finally sorted out just about everything to do with Treasury business. The one outstanding thing is Bank of America promised it would be easy for outgoing Treasurer David Baranski to cancel his club credit card, and it's not easy. They lied about that. So he still has an open credit card, and I'm tempted for him to just cut it up and mail it to me, but that won't get it off his credit report. So it should be his credit. Well, maybe I'll just ask for it in a bag because the process for canceling the credit card is surprisingly silly. Other than that, we still need a secretary. We have not had a secretary since February. Dale, Teamy, and AI have been doing an excellent job of capturing the spirit of our meetings, but as a confirmed AI skeptic, I'd rather have a human being powering our minutes. And ultimately, we do need that seventh vote on the board in the event of a tiebreaker for something contentious, like, say, insurance on Stargate, which comes up every year. So, if you are interested in being the club secretary, I promise it's relatively painless. And just let me know or email board@warrenastro.org and say you are willing to join the party. We have gotten some volunteers lately for snacks. Parker and Ruth Humantle very nicely brought snacks to the Cranbrook meeting. Some of their bounty is still here at Macomb meeting. I purchased a few things to eke that out. So we've got snacks tonight here at Macomb. But if you are interested in bringing snacks for Cranbrook, just let the board know, and we will reimburse you if you choose to be reimbursed. If you choose to take it as a donation, thank you very much. We appreciate that too. And with that, we've got very few outreach events on the calendar other than Stargate open houses. So I don't see Jeff on the call tonight, so I will just say that I want to hype Cranbrook in August. We've got a partial lunar eclipse, a partial solar eclipse, and theoretically solar observing. And Perseids. And the Perseids and the partial solar are the same day, the 12th. Yes. So they want us all day at Cranbrook on the 12th. And then regular observing on the 27th. So mark down your calendar because we're hoping for a real good turnout for August and we're hoping for real good weather. Okay. With that, I'll turn things over to the first Vice President, Jonathan Cade.
Uh, for the upcoming programs, we have only about 5 slots left in the year. We still have the banquet speaker unfilled for December. So if there's somebody that you would like to hear from local institutions or people who we could ask to speak, please let me know. And I'm working on some ideas. But if you want to present, the slots are running thin, so let me know as soon as possible. Next month, we will have the redoubtable Ken Burton presenting a biography of Charles Messier, and I'm trying to get him to also include his favorite Messier objects. And I will be preparing for him by demonstrating my 10 favorite Messier objects and also my 5 least favorite Messier objects and why they're maybe not that bad after all. And for the uh, for the Thursday, we are going to be from Macomb next month. We're going to be hearing about visiting the Canary Islands and the telescopes there from both Hollenbaugh. So we will have a really special travelogue. So looking forward to that. And that's it for me.
All right. Thank you, Jonathan. Jonathan mentioned the banquet. As I said at the previous meeting, the banquet date has changed from what was posted on the calendar. Instead of the 10th, in order to make the second week in December less cluttered with WAS stuff, we moved it to the 17th. So we're going to have the banquet at the Ukrainian Cultural Center on the 17th, and we're going to have the picnic, as y'all know, was originally supposed to be in August. It was moved up to July because of a conflict with the pavilion at Stargate. So the dates on the calendar, I regret to say, are not accurate any longer. One might call them inoperative. So picnic July, banquet December 17th. 25th. Same night as the Stargate open house. Yeah. 25th. All right. Riyadh is on the call. Over to Riyadh for the observatory report.
Yeah, thank you, Diane. Hello, everyone. Last Stargate Open House was on April 25th. Unfortunately, it was cloudy. We opened at 7:30, and it stayed cloudy until we closed at 9:45. We still had about 20 people visiting us, and we had 6 members actually attending. So since we couldn't observe, we just talked about astronomy, talked about the telescopes that we have, and answered the visitors' questions. I had, of course, a lot of help as usual, thanks to Jeff McLeod, Tina Wong, and Dale Martin. They helped answer questions, help work the small crowd that we had. The next open house is coming Saturday, started at 8 p.m. So May 23rd. Hopefully we'll have maybe better skies. It doesn't look that way right now, but we'll see. Even if it's cloudy, I'll be there, of course. So at least for 2 hours, come on out and we can talk about astronomy. And if you have questions, we can try to answer them. Also, I should mention May 2nd, we had an open house for a number of scouts that requested that open house, and had Jonathan and Diane came out, as well as Bob Berta and Dale Parton. They all helped out. Jonathan also helped with the closing and opening of the dome. And he set up the 22-inch Dobsonian outside for observing deep sky objects. And inside the observatory, we used the 8-inch refractor to look at Venus, Jupiter, and some double stars. We had about 40 people, maybe total, that were out there. So come on out this coming Saturday, and hopefully we'll see everyone out there. Take care. Thanks.
All right. Thank you, Riyadh. As I said, we do not currently have a secretary. Our treasurer, Mark Miles, was intending to be here tonight, but I don't see him. Treasury report is in the WASP as usual, so look for an updated one in the WASP to be published next week. We're almost to the end of May. Outreach. I covered outreach since Jeff couldn't make it tonight, and as far as publications goes, send in your articles, drawings, poems, photographs, and whatnot to publications@warrenastro.org by the 28th of the month to be in the upcoming June WASP. Did I miss anything? All right. That takes us to subgroups, and I believe we have a solar update, courtesy of Bob Tremblay.
How many astronomers does it take to share a document?
I'm already sharing the screen.
Oh, are you? Oh,
Yeah.
the solar report?
Yeah.
Yeah, we
Oh,
see it.
look at you.
Look at Dale.
Okay, so from spaceweather.com, not alarming or anything. The far side danger is subsiding. New data from Europe's solar orbiter show that a massive far side sunspot group first detected last week is now dispersing. The sunspot has not produced an X flare in 5 days, meaning it did produce an X flare in the last 5 days, and even M-class flares are becoming scarce. The sunspot may pose no danger to Earth when it turns toward us next week. The solar wind is low. There's a couple coronal holes you see right here in this image of the purple image. That is SDO 211 angstroms. We've got a coronal hole kind of facing us, a small one, and a larger one rotating into view. Solar wind pours out of those things. So this morning we scroll down and see the full. Yeah, there you go. That was from this morning. There are one, two, three, four. Yeah, four numbered sunspots. All of them are quiet and pose little threat for strong solar flares, according to NASA. NOAA reported a couple C-class flares over the last 24 hours, so that's really tiny. Continue down. There you go. Coronal loops. You got a lot of coronal loops in the northern hemisphere, and a pretty big one at the 8 o'clock position on there. And now for something completely different. Keep going down. The famous Earthrise photograph from Apollo 8 had an asteroid named after it, so asteroid Earthrise. And there are all the specs it says here. Earthrise is a photograph taken by astronaut William Anders in 1968 during the Apollo 8 mission to the moon. Showing Earth above the lunar horizon, it changed humanity's perception of its home planet and became an icon of the environmental movement. The asteroid was discovered on the 30th anniversary of the photograph. So that is from the IAU. And from when I was looking at the Minor Planet Center, I just scrolled down to see if there's any asteroids that came within a couple lunar distances, and one of them came within 0 lunar distances. I'm like, oh my! So a 1 meter asteroid designated 2026 JN4 entered Earth's atmosphere. Is it Papua New Guinea? Is that how you pronounce that? Papua New Guinea. On May 16th, it was discovered the day before. No footage of an atmospheric entry has surfaced and no ground impact. So that's solar and a little bit of asteroid stuff.
Excellent. We've got a report from online that our sound is cutting out. Which microphone are we supposed to be using?
Test check, test check. Test check, test check.
Now you're coming
Can I
clear.
get a test 1, 2? A test 1.
Yeah, you're coming in clear now.
Okay. Good to know. All right. So, double stars. Riyadh, we actually have something to talk about thanks to that clear night we got with the scouts.
Yes, we did look at a couple of double stars. That was really good. We looked at Castor, and also I forget the name of the other star. It's in Leo. The other thing is I was trying to do some astrometric eyepiece calibration, but the battery was dead. So I have fresh set of batteries with me. I'll install them for this coming open house. The other thing I want to do is to dim out the astrometric eyepiece light illuminator, the reticle illuminator, because it's just way too bright. So I'm going to try to do that this weekend. So we got a few things to do, and hopefully we'll have something we can use at the next clear open house and do some calibration and then do some measurements.
Excellent. Well, hopefully the skies are going to be better than predicted on Saturday night. Let's see. I do not see Tom Hagen, our radio subgroup captain. And astrophotography, anything to report?
This means you.
There are some telescopes coming out, but I would wait until reviews come out on. There, TWO is gonna be coming out with an AM7, which is 60-pound capability, load capability, and it's again a small, very small. I think it's gonna weigh probably maybe 12 pounds for the mount, which is incredible. So that should be coming out pretty soon.
Nice.
There is also TWO, the S series, like the S3850. There's a couple more of those coming out, new ones. It's going to be an S, I think it's an S60 or X70, also larger, slightly larger one. And then they're going to eliminate one of them. I don't know if they're going to come out with a new version of the same thing on one of them. I think it's 30. They're coming out with an updated version of that. Other than that, that's where it stands now.
All right. As a reminder, if you have a particular passion, urban observing, computers, what have you, approach the board and you can found your own subgroup and be a subgroup captain. It takes basically 2 people to be a subgroup. Speaking as a former member of the urban observing subgroup. Let's see. Yes, we have our special guest tonight, so over to David Levy for poetry.
Well, thank you very much. It is a pleasure for me to be here tonight. I wanted to tell you a little bit about a telescope that I've had since 1967. It's called Minerva. It has gone through 4 different changes of mounts over the decades and about 12 different changes of tube assemblies, but is now back to the original tube, which I'm now using and enjoying. My quotation tonight is from one of my favorite American poets, Walt Whitman. And it is from his lovely poem, A Clear Midnight. This is thy hour, O soul, thy free flight into the wordless, away from books, away from art, the day erased, the lesson done. Be fully forth emerging, silent gazing, pondering the words thou lovest best, night, sleep, death, and the stars. Thank you very much, and back to you.
Thank you so much.
This kind of sounds, David, like you've got the telescope of Theseus there.
So speaking of the stars, do we have any observing reports? Any observing reports here in the room at Macomb?
I was able to get out on the 11th and I think 16th for pictures of M81 and M82.
Nice.
And M101.
Pictures of M81, M82, and M101. Excellent. If this is the time of year for that. Anybody else got any observing to report other than clouds? We all observed clouds. Bob,
Clouds.
clouds.
That's sorry.
You said
Other
okay.
than clouds, sorry.
That's
sorry.
okay.
We have a couple of photos
Yes, we do.
on the desktop.
Nice.
M101.
Pictures of M81, M82, and M101. Excellent.
Oh,
This is the
where do
time
we
of
have?
year to want. Anybody
the-
else got any
Where's the
observing to
echo
report
coming from?
other than clouds? We all observe clouds. Bob,
Somebody's watching Zoom. Or it's on YouTube.
All right.
Oh, okay.
Can we mute? Oops. Would you like to talk about your?
Yeah, let me talk. I got 3 pictures here. So, Jim Wallace here. I like to do a lot of reuse of different things. And so one of the biggest hassles is always about when you're going somewhere, carrying the darn weights, right? And so I had this is actually an oxygen caddy that I started with that I had from when my dad was around. And so I thought, let's see what we can do with that, and so you can do can you hit the next picture there? There's 3 pictures. Where's the next one?
Click back on the photos
Oh,
down.
so anyways, you can probably just go, yeah.
That's the photo.
Oh, here we go. You
Yeah.
can just stick with this one. Okay.
But that one's not sharing though.
Oh, it's the thing back.
oh,
Is it still sharing?
All right. Oh, you gotta hit the next.
Oh, why does Windows have to ruin everything? All right, this is the one you wanted?
Yeah, it's okay.
All right. If anyone would like to propose that the club get a MacBook Neo, we can take that.
All right, people see that? So here you can kind of see how it actually works excellent. You stack the weights on there, you stick the pole in between. If there's a little, you can't really see, there's a little cotter pin that kind of holds the pole in place. And when you're traveling and going places, you could just wheel your weights, and it just was a clever little thing. I thought people might be interested in. If you have one of these old auction things from maybe your parents or something laying around, it's a very simple project and to make something that's extremely useful. So
nice.
that's,
Thanks. That's cool.
We have a bird on the call. All right.
Is that a video? It looks like the grass is moving.
picture, yeah.
Close your screen.
Close the share screen.
It's a real bird outside. Wow.
Or do you close the share screen?
The X.
Oh, there.
Yeah.
Okay. What?
Sure. Take a picture of a lot of things in the backyard.
I'm trying to adjust the camera.
Picture. But you don't see the picture move, but it's obviously the weights don't move.
Okay.
Unless you take them out.
All right. So any other observing reports on clouds don't count?
And it's not an observing report, but it's a chance to observe. Sure, public every year in Rochester Heritage happens. It's a 2-day event with thousands of people coming to it. And the Oakland Astronomy Club, which I also belong to, does a lot of solar astronomy demonstrations there. We have multiple solar telescopes set up doing video. We also have Tom Hagen usually has his radio telescope stuff, so we can actually, demonstrate how a radio telescope works. Was it last year or the year before? We were privileged because we actually had a coronal mass ejection, which we were able to see with the solar scopes we had. Plus, through Tom's equipment, he was able to actually use the audio show on a screen what you're actually looking at, seeing it. So you got a chance to demonstrate how a solar astro event would be seen. And that runs both days on the was it the 30th and 31st of this month. And it starts probably around 11 o'clock, 11:30. It goes on till around 5 or so. And there's all kinds of events in that park. There'll be a car show. There's going to be cooking, music groups playing, kids dance groups, and everything else. So it's a really cool event. So if you got that free, hit the Rochester and you can drop by and take a look through the various telescopes and see how it's done.
Sounds like fun.
Can you say what part of the festival you'd be set up at? Area? Or the area, what area will you be set up at?
It's kind of near the back of the park. Everything is set up like in a line. And we're at usually that's far in. We're at the along the river.
Fabulous. Any other observant reports or events to pitch?
Do we need to start the break?
Yes. Well, we're closing in on 7:30, so it's time for our snack break. Since we've got actual physical snacks here at Macomb, we're going to take about 15 minutes. Reconvene at
10 minutes.
10 minutes. Reconvene at 7:36.
Launch is going to happen in about 3 minutes.
Yeah.
And I'll turn things over to Jonathan so that all of you can watch this launch that's happening.
Kalée, did you want to share the video? If you
Oh, sure, I'm happy to. This is happening, let's see. In I don't even know where it is. But it's happening somewhere near an ocean. And SpaceX is doing a Starship flight test, I guess. That's all I know. I'm just reading the captions. But it's gonna happen in 3 minutes.
Yes.
Quickly present to sit down. Hi. Nice to meet you. Great. Yeah, no worries. We have people from my people come from Berkeley and Pittsburgh. We're finding.
And you're from Powell, it's a line to launch from the Brady. You put it, Karen.
Oh, I could turn on the
Kalée, would
sound. You want me to turn on the sound? Here.
Yeah.
Minutes, we have completed propellant loading on the booster. Just shut down the fuel pump for loading onto the ship, so we're closing all of that out now. 2 minutes ago, one kind of exciting aspect of V3, we're not going to start the engines up in kind of different sets. All 33 of those Raptors going to turn on all at once. You're going to see the booster move off the pad a whole lot quicker.
Once again, if you've just joined us, this is the first flight for version 3 of Starship. The ship, which is the upper part, the black part there at the top, the booster, which is the part below that, have been completely redesigned, as well as the launch pad that you see it sitting at, as well as the engines that power both the ship and the booster. Today's test flight is a massive step forward in our developmental program.
All right, and we're coming up here on T-1 minute. So let's go to the pad and let the rocket do the talking as V3 fully comes alive. T-1 minute. Right, so we did hit the hold at T-40. Again, this is something that is built into the timeline. Not surprising, as we are doing this first flight off of pad 2. Sounds like we might already be clear. We held for a second just to make sure that the quick disconnect vents were basically ready for their final throwbacks. We'll hang tight for a couple of seconds. I think we're about to reset, and the reset is in. Counting down, first flight of Starship B3. Site back to rapid recycle. All right, so hold here for a second. Looks like we're still managing some pressures in the ship quick disconnect. All right, still gonna hang out for a couple of seconds here at T-40. Again, not surprising. This is new vehicle, new pad, doing all these things for the very first time. Right now we are holding, looking at some pressures in the quick disconnect and hold reset, and we're rolling.
Flight directors, go to launch.
Back to rapid recycle, so we're gonna hold at T-40 again. Stay for a second, we'll see what tripped this last one. The reminder, we can hang out for quite a few minutes at T-40 if we need the extra time. You're not actively loading propellant onto the vehicle anymore, so the main thing you're kind of keeping an eye on is all of the temperatures inside those propellant tanks. We're continuing to hang out here at T-40. He's taking a look right now at our diverter, so that water diverter underneath the system did trip a hole, but that basically just gives the team a chance to look at it, see if it's something that we need to troubleshoot in data or if it's something that we can clear this hole. So continuing to hang tight, T-40 seconds. Starship and Super Heavy fully loaded on the pad. Clock is rolling.
Go at 30, flight directors, go for launch.
Kick back to rapid recycle again.
They're teasing us.
Again, just a reminder, set up before, new pad, new rocket, learning new things about this hardware, performing in the flight environment. Taking a look at some of the sensors on the arm that manages the quick disconnect to the ship. I promise we're not just trying to prolong the anticipation. Team's taking a look.
Oh, sure. That's what they all say.
Got a couple more minutes where we can hang out here. Again, it's not an unlimited time to pause at T-40. We're keeping an eye on the propellant temperatures inside the vehicles. So we've got probably about 3 minutes or so left of hold time.
So
Seems
Yeah.
to look at
Kelly, I would, I guess, defer to you on whether you want to
disconnect.
give them more time or if you want to get started.
Well, I guess he said that they had like a limit of 3 minutes of hold time. So it seems like if they don't do it in 3 minutes, they're not going to do it. So maybe we just give him those three and see what
Sounds great.
happens. It would be
Yeah,
hard
just-
to stop now. We're so close. My
Yeah,
talk is
we're
like 45 minutes, so it won't be
okay.
that long.
Yeah, we should be fine for time. I just don't want you to, feel like you
No, I
got
want to
roped
see
into
this
being the
too.
YouTube.
Yeah. Yeah, we're streaming another stream, I guess. Okay. It's like all of this whole recursive thing, but yeah, let's see what they do. In 3 minutes, if they haven't gone, then maybe we'll assume it's not gonna happen. But
Stanford. Pardon me? Stanford.
D minus 40, still troubleshooting this issue. We got about a minute or a minute and a half left of the whole time.
Exactly, go or no go.
I imagine like nobody wants it to be like their decision. Can you imagine if you had to decide, like that everybody's waiting for this thing to launch, but if you call it wrong, everything might explode.
Also, I suspect, your boss might not be the most understanding person in the world, is the impression that I get.
Indeed.
Sure. Of,
And that's being, polite.
I'm going to the bathroom, don't go off now.
All right. Tom Cervinek is taking one for the team. He's going to use the restroom so that they can take.
He's risking missing it. Well, I was so excited to hear that you are looking at double stars. Do you ever submit those measurements to the Washington Double Star Catalog?
That's a lifelong dream. It hasn't
Yeah.
happened.
Oh gosh, it's once you make the measurements, it's not as hard as you might think. In fact, I do it with students sometimes, which is really fun. And it's amazing to do double star work because some of the orbits, as you know, probably are so very long that that every measurement is useful. That like even the ones from long ago in the 1700s when they started doing it.
Correct. Yeah, there are a number of what's called neglected doubles.
Yes.
And we used to do this. I used to do this back in the mid 80s.
Still continuing to hold here
using a bifilar micrometer. But you can't
yeah.
find those anymore. Now I guess people are doing it with cameras.
Yeah, well, we do it even with robotic telescopes. We use the Las Cumbres telescope network, and it takes just a small amount of telescope time to get a bunch of images. And actually, AAVSO, which I'll talk about, has a network of telescopes that can be used remotely as well to get. Oh, we're rolling. Okay, I'm going to put this back on. Oh, and we're stopped again.
We're back in the rapid cycle.
They might accidentally go to Mars.
Yeah, right. Well, let's see. I could.
Back at our T minus 40.
All right. Thank you so much.
Bye.
Thank you for coming.
What Trip does this time?
Well, I am happy to I'm happy to get the ball rolling if you are.
Okay, yeah, I'll start rolling and then if anyone notices this thing coming back, we can come back to it. But I'll start out talking about exoplanets, which is, are we rolling again?
Yes, may I quickly introduce you
Oh,
before we
sure. Yes, of course, of course.
yeah, so thank you all for being here for the feature presentation. Kalée Tock started a PhD program for chemistry, but decided to stop with a master's degree when she realized she liked teaching more than research. She completed a second master's degree in learning design and technology and now teaches science at Stanford Online High School. Her special passion is designing science experiments, some of the best ideas for which have come straight out of the lab notebooks of her curious and creative students, and has launched 4 high-altitude balloons. She also has a wonderful family, including her husband and 3 children. Thank you so much for joining us, and she is joining us from Stanford, from California. So thank you so much for being with us.
Thank you so much for having me. I'm so excited to be here. I thank you, Jonathan, for that nice introduction. So I'll start by introducing myself and telling the story of my journey to astronomical research. And then by the end, if all goes according to plan, we'll end up on an exoplanet far, far away. So here goes. I never used to think of myself as a science person. I, at one point in my youth, wanted to be a minister, and I kept taking religious studies classes well into college, even after chemistry began to seduce me away from religious studies. And then I started, as Jonathan said, the PhD program for chemistry at Stanford. But within about a year and a half, I figured out that I enjoyed teaching more. And then I spent a couple of years while I was still technically part of the chem department taking classes in everything from computer science to philosophy to education. And I funded those classes in my grad student lifestyle by taking a job as a teaching assistant for an interdisciplinary core course called Light in the Physical and Biological Worlds. One of the lab managers for that course was, and I think still is, a developer of exhibits at the Exploratorium, a science museum in San Francisco. And her passion for science and sense of fun were a huge inspiration to me. So then I transferred to the Stanford School of Education. I earned a second master's degree there, and on the side, I taught the chemistry and physics sections of the Princeton Review's medical college admissions test prep course. And that was fun, but there were no labs, and hands-on labs are kind of my thing. So I had at that time an internship on campus that became a job doing data analysis for what was then called the Education Program for Gifted Youth. During these years, I got married and had 3 babies, who, as you can see from the slide, are not babies anymore. The Education Program for Gifted Youth spawned the Stanford Online High School, where I now teach. And they, at one point, had an announcement come around to the staff mailing list that they were seeking a chemistry instructor, so I knew I had to apply. I taught there for a few years. I loved it. I've always loved interdisciplinary science, and I've always had like a recreational interest in astronomy. And at staff meetings, I kept on saying things like, English gets to have eclectic classes like film studies, so science should get to have eclectic classes too, like maybe astronomy. And then about 10 years ago, Dr. Kim Failer, my division head at the time, told me to stop complaining and put my money where my mouth was. And that was the beginning of this journey that has taken me to more strange and beautiful places than I ever could have imagined. And my career as an astronomy instructor launched with the first in what would become a series of 4 high-altitude balloon launches, which could be their own talk. But I believe that science in general and astronomy in particular scratches the same itch to ask big questions that brings people to church. So I feel like I have fulfilled my childhood ambition, even though my ministry is not at all what I would have envisioned. Learning and teaching about how the universe began or didn't, or what the implications would be if we were to find evidence of life on an exoplanet, strays unavoidably into philosophical territory. This image is one taken by the Voyager spacecraft, which was launched in 1977, and since then has traveled 16 billion miles, or only 0.0027 light years. But it's still the most distant human-made object, and on its way out of our solar system, it snapped one final picture of Earth before our planet was forever lost to its view. And contemplating this image, Carl Sagan famously described our planet as a pale blue dot suspended in a sunbeam. So, what can we learn from a pale blue dot? Well, we can learn whether there are clouds or maybe oceans. We might, over 24 hours, see variability because of different fractions of land and oceans. And over the course of a year, we might see it block the light of its host star if we're in the right orientation. We could do spectroscopy on the atmosphere and get a clue whether this pale blue dot has very much oxygen or methane, and we could tell whether there are plants by the color of the dot. Maybe you don't think of plants as blue, and they're not. We commonly think of plants as green because they reflect green light. But if that's the criterion, plants aren't green, they're infrared. They reflect much more infrared light than they do green light. So if we could see in the IR, we could tell by the infrared color of our planet that we have plants. And that's why IR is the best region of the spectrum to study exoplanets, and it's why the James Webb Space Telescope, which uses infrared cameras, is so valuable for doing so. But even James Webb has a hard time seeing the pale blue dot directly. Usually it does the same thing we do from the ground, which is to take images and spectra as the planet transits its host star, looking for clues about the planet from subtle features in the dip of the starlight that it blocks. And for this to work, the planet has to block starlight from Earth's perspective. So the planet has to cross between Earth and the star during its orbit. So the easiest planets to study with modest size telescopes are planets that orbit frequently, where frequently means every few days, and make big dips, where big means that they decrease the observed brightness of the star by 1% or more for the few hours during the transit. So, and to orbit frequently, Kepler's laws tell us it has to be close to the host star, and to make a big dip, the planet has to be big, like really big, like as big as Jupiter big. And Jupiter's radius is 1/10 the sun's. Area goes as radius squared. So if you divide the area of Jupiter by the area of the sun, you get that it blocks 1/10 squared, or 1/100th, or 1% of our star's light. So you need a Jupiter, but you need one that's close to its host star, or a hot Jupiter. And hot Jupiters are weird because they tend to be made of icy and volatile molecules, the kind that are typically blasted far away from the star after it ignites because they're so light and vaporous, and they're not thought to be able to accrete into the core of a planet close to a star. So the big question is, what are they doing there? In our solar system, gas giants are found in the outer solar system where they belong, but extrasolar systems seem to have a lot of gas giants that are abnormally close to their star. So one explanation is that maybe they form farther out, but then they collide with stuff and lose orbital energy and migrate inward. Or maybe they're actually really rare and they only form under very unusual circumstances. And the reason that we seem to see so many of them is that they're the easiest to see because they're big and they transit often. You need at least 3 transits to confirm an exoplanet, and the first ones were discovered in the 1990s. And in our solar system, Jupiter has a 12-year period and Saturn has a 29-year period. So it would take 24 years to confirm Jupiter if we're lucky enough to capture a transit in year 0 when we start observing, and 58 years to confirm a Saturn. So there might be bazillions more normal Jupiters and Saturns out there than there are hot Jupiters, and we just haven't confirmed them because we haven't been looking for a long enough time yet. We don't have a good feel for the statistics of this. We don't know how much our selection bias toward things that are easiest to see influences our inferences about what's out there. Whatever the statistics may be, to figure out what's going on with these hot Jupiters, we've got to study them. And this can and is being done with space telescopes, but small backyard telescopes are also essential to the process. We said that hot Jupiters have short orbital periods, like a few days. And if the orbital period is off by 10 seconds or 0.0001 days, then over 10 years or so, the mid-transit time might drift by as much as several hours. And if you point your telescope at the target several hours too early or too late, it'll cause you to completely miss it. So we have to keep observing transits to keep NASA's prediction of the next transit time, what we call the ephemeris, fresh and accurate. And at this point, there are thousands of known exoplanets to keep track of. So it's too big a job for any one observer or even any one space agency to do alone. NASA relies on amateur astronomers and school groups to keep making measurements. And there are also uses for continued measurements even beyond keeping the data fresh for space telescopes and large ground-based telescopes. For one thing, there are TTVs. So if we measure a transit and then the next time we measure it, it's late based on the orbital period we've calculated. And then the next time it's a little bit less late, and then it's early, and then it's a little less early, and then it's late again. That's what we call a transit timing variation, or TTV. And TTVs might happen because the planet's being pulled by something like maybe a moon or another planet in the system. We might not even see the object doing the pulling because it's too small, or maybe it hasn't transited yet, or maybe its orbit isn't in a plane between us and the star. But we can tell it's there because it affects the midpoint of the object we're measuring. And even variations in the transit duration, or the length of time that the planet spends transiting, can indicate the presence of another planet in the system. So in this case, this red planet is being tugged on by the blue one here. And you can see that due to the influence of the blue one, its mid-transit time is not exactly on the dot of when it's predicted to be happening. So that's one reason for what we call TTVs, or transit timing variations, is another body in the system. And then the second reason is what's called apsidal precession. And this is an effect of the warping of space-time near a very large mass, like a star. And it's caused by relativity. It's a prediction of Einstein's. We've observed this in our own solar system with the planet Mercury. And hot Jupiters are really close to their host stars, as we've said, so their orbits are also predicted to precess because of general relativity, and this will lead to slight variations in their mid-transit times that would provide some evidence that this is indeed happening. And then the last reason, actually there are probably more, these are just the main three that I know about, why a transit timing variation might happen is that its orbit is decaying and the planet is in the process of spiraling in toward its host star. And that's more common with hot Jupiters because they're close to their host stars to start with. And because they're so close, there's a big difference in the gravitational attraction of the near side of the planet to the star and the far side of the planet to the star. And that difference is called a tidal force, and it causes both the planet and the host star to distort and oscillate. And that converts the planet's orbital energy into heat within the star. And it also exerts a gravitational torque on the planet that causes the orbit to decay. So these are three reasons why transit timing variations might happen, why they're interesting and useful. But in order to find them, you need a lot of astronomers measuring a lot of transits. And that brings me back to why we've got to keep observing these exoplanets and contributing as much data and analysis as possible to NASA. So how do we do it? Well, you can search up the Swarthmore Transit Finder and enter your latitude and longitude and specify that you want at least a 1% transit depth or 10 PPT because they do things in PPT on that website. And it'll show you all the planets that will be visible from your location for the next 3 nights. And it tells you when to start observing in local time or in UTC if you roll over the time window. And from your WAS website, it said you often observe at Stargate Observatory that you mentioned earlier as well. So I put in that latitude, longitude, and from this screenshot, you can see that if you head over there shortly after this and get set up by around 10:20 local time, you could catch WASP 103b, which is a magnitude 12.4 host star with a planet that has a depth of 1.2%. And you'd have to miss the planet's ingress into transit because it was a little too close to the horizon earlier. That's what that dashed line means. But if you take a little more time to get set up, you could get HAT P12b starting just after 10 p.m. or TOI 4145 AB starting a little after midnight. And by the way, TOI stands for Test Object of Interest, which means that this target was discovered by the TESS Space Telescope. But if you need your beauty rest, there are a bunch of robotic telescope networks I was mentioning earlier. If you're a member of the American Association of Variable Star Observers, or AAVSO, you automatically have free access to AAVSO-Net, a worldwide network of research-grade telescopes which operates on a proposal system. There are lots of other telescope networks. My colleague Michael Fitzgerald hosts a network called Next Astro, but that's not free, but it includes a bunch of resources in addition to telescope time. And if neither of those work for you, NASA Exoplanet Watch has a free data checkout system hosted by the Harvard-Smithsonian Micro-Observatory that you can use, which brings me to AAVSO and Exoplanet Watch. NASA can't store all your images. Usually, for many astronomers, storing images has become more and more of a problem. None of us have enough storage space. Those image files are enormous, like hundreds of megabytes each sometimes, and astronomers store data in different formats, and every astronomer thinks that every other astronomer's formats are wrong. You can tell I use a lot of different data sources when I do exoplanet transit reductions. So in any case, rather than several gigabytes of images for each transit, the important information that NASA needs to store is just enough to capture the transit midpoint and the shape of the curve as succinctly as possible. So they want a text file. They want 4 numbers for every image: the time of the image, the light from the star, 2 numbers that describe how much of Earth's atmosphere the light went through, or the air mass. And the AAVSO maintains the database of exoplanet host star observations for NASA Exoplanet Watch. AAVSO is a worldwide scientific and educational organization of amateur and professional astronomers who are interested in stars that change in brightness, variable stars. And that might happen because of stuff happening inside the star, or because they have a planet that temporarily blocks them from Earth's line of sight. So membership in the AAVSO is open to anyone who's interested in contributing to variable star research. Professional astronomers have neither the time nor the telescopes needed to gather data on brightness changes of thousands of variable stars, and amateurs make a real and useful contribution to science by observing variable stars and submitting their observations to the AAVSO International Database. So if you want to contribute exoplanet data to NASA, make yourself an AAVSO account and request an observer code. You don't have to join AAVSO to make an observer code. That part's free. You do have to join AAVSO to use the AAVSO telescope network. Membership for students is discounted, and yeah, but you don't have to even be a member to have an observer code. Okay, so let's say you get images from somewhere. You get them from AAVSO.net, from the Exoplanet Watch data checkout system, or you head over to Stargate after this talk and get the images for yourself. So first, we have some images. What now? Do we see the star in this image that has a planet going around it? No. So we need to identify the target. There are several ways to do that. It sounds like you probably have ways that you're familiar with. You could plate solve it and then just mouse around until you're on the right coordinates. And another way, which I use with my students, is to go old school and match up the coordinates using a star chart from the AAVSO. So this is the AAVSO variable star plotter, or VSP, which plots the stars in a region that you define using the coordinates of your target. So you just enter the RA and DEC onto the AAVSO site. It makes the star chart, and you can look for patterns and match up the stars. So in this case, there's the target. The yellow box shows it. It wasn't rotated or flipped, which is helpful. But now we have to find that star in each of our hundreds of images and measure its light, or photometer it, and then we can plot that photometry of the star as a function of time and look for the dip when the planet passes in front of it. But it's not exactly that simple, is it ever? Over the course of several hours, our own planet, Earth, keeps spinning. And from the perspective of the telescope, the star might be getting closer to the horizon or zenith. And it might, either way, it's not going to stay in the same spot. So if it's getting closer to the horizon, its light will pass through more atmosphere on the way to the telescope. That'll make it look dimmer and redder, the same way the sun looks dimmer and redder when it's near the horizon. And if it's getting closer to zenith, it will become brighter and bluer. So all of that means that if you just plot the brightness as a function of time, you get something that looks like this. This target was getting closer to zenith over the course of the observing run. There is a dip there. You can see it if you know what you're looking for. But we're not interested in the way the Earth's atmosphere was changing. We're interested in how the starlight was changing. So that's why they want those air mass numbers. We have to correct for the amount of atmosphere that the light is going through on the way to the telescope. And that's not the only atmospheric effect we have to correct for. There might have been some high, thin clouds that rolled in during the observing run, and you might not have even seen them. They might be invisible to the eye. Maybe they only affect the light of the target by like 2%, which is only, oh yeah, that's the size of the dip we're looking for. So to correct for those other atmospheric effects, we use a comparison star, or comp star, which I'll talk more about in a second. But in any case, if we do all those corrections properly and we pick a good comp, we can turn this plot into something that looks more like this. And so to get from here to here, we have to know what a comparison star is and how to pick a good one. And because as we see, just plotting this raw flux from the target makes a wavy line with just a suggestion of a dip instead of a light curve with distinct features. But presumably other stars in the field were subject to the same increase in flux over the course of the observing run. Here's the flux of one of the other stars in the image plotted over the same interval. And you can see this one is straighter. It doesn't have the wavy curve. So what we can do is compare those two raw flux measurements, and then you can really tell that the target had a dip and the comp didn't have one. And there's a lot more to say about calibration, but for now, let's just make sure that the comp star is not itself variable, because if the comp is pulsing brighter and fainter, or the comp has exoplanets that's circling around blocking its light, we're going to mistake that for what's happening to the target star. And so how do we know whether the comp is a variable? Well, we don't, but AAVSO keeps records that can help. Any star with a number on one of the star fields from AAVSO is a recommended comparison star, meaning that it's one a lot of people have observed and they've studied before and they've found it to be constant. Okay, so say you find the target in the star field and it's labeled in green on this inverted image, and you chose a few possible comparison stars, which are labeled in red. Now you need to define the same region around each one, which is called an aperture, and count all the photons that struck the sensor within that circle. And then you need to do the same thing for each of a couple of hundred of images in your series, and then take the ratio of the brightness of the target to the brightness of the best comp for every one of the images and plot that over the course of the entire observing run. So that'll be fun, but luckily we have software for this. It's called Exotic. And caveat that you don't have to use Exotic if you do this sort of thing on a regular basis and you like software like Astro ImageJ or DS9 or Afterglow, you can use one of those. But Exotic is built especially for analyzing exoplanet transit, and it runs directly on your images, and it can do that in the cloud on Google Drive. So I'm a fan of Exotic, but it's not necessary to use it. Astro ImageJ is perfectly fine, and you can use that as well if you're familiar with that and like it better. So you do have to find your target in the comps in the first image of the series, and you specify their pixel coordinates in X and Y on the image. And then Exotic has algorithms that'll follow those stars whose pixel coordinates you specified through the whole series, as long as the telescope doesn't move too much between images, even though it still is able to track them somehow after a peer flip, which is amazing. But in general, yeah, as long as they don't move too much, it'll be able to find it if you just specify where they are in the first one. And then to fit the light curve, it needs information about the observatory your images came from. It needs other information like what filter you used, because the transit might look very different in different filters. It needs information about the planet, like its known transit depth, its duration, the shape of the curve, a whole bunch of things about the properties of the host stars. And that's because the light curve that it generates uses what's known about the host star and its planet to inform what are called the priors of its fit. The priors are the parameters that define what the light curve is expected to look like based on what's already known about the system. So this gives Exotic a starting point for fitting, like how sharply the curve dips and how flat its bottom is and how long the eclipse lasts, et cetera, et cetera. And once it finishes fitting your data, it generates a data file for you to upload to the AAVSO that has all the times and brightnesses and air mass parameters and such. And the midpoint of the transit on the night your images were taken will be one of the posteriors, which in turn informs the priors that Exotic uses for future fits of the same system. And Exoplanet Watch uses the analysis of observers like you to update the priors for every exoplanet system every few days. They literally take all the data that has ever been submitted and they rerun all of their fits with updated priors so that the posteriors can be known as precisely as possible with the smallest possible uncertainty. But one thing that prevents the uncertainty from getting as small as we might like is the host star. Pretty much all stars are variable on some level. They can swell up and shrink down and change color and orbit companion stars and rotate and have star quakes and star spots and all sorts of things that make it really hard to know which parts of the brightness change we observe are due to the planet blocking it and which are contaminants, i.e. other stuff. The mantra is know thy planet, know thy star. And there's a mission that just went up a few months ago called Pandora, which was actually, I think it's out of the commissioning phase now and has started taking images. And its goal is to observe exactly just the host stars of 20 exoplanet systems. It has a 0.45 meter telescope. It's in low Earth orbit. It can do visible photometry and infrared spectroscopy. And the whole goal of this mission is to disentangle star and planet signals in transmission spectra so that it can reliably determine exoplanet atmosphere composition. And so it has like two sub goals. The first is determine the spot and faculae covering fractions of low mass exoplanet host stars and the impact of these active regions on exoplanetary transmission spectra, which is a fancy way to say find the star spots. And then the second is to identify exoplanets with hydrogen or water dominated atmospheres and determine which of those are covered by clouds and hazes. So it has these 20 targets for long durations. It's like basically going to look at 10 transits per planet. The sizes range from Earth size to Jupiter size. The host stars are mostly red dwarfs, mid-K to late M spectral types. And the target list is published on the website. It's super easy to find it. And many of them are observable with small ground-based telescopes. And they actually really want simultaneous ground-based observations of these targets, both in transit and out of transit, because they're looking for long baseline variability information. They're looking for rotation rates and star spots. That tends to show up especially well if you can use different filters at the same time. And I had a team last semester of students in my project-based research seminar working on looking for star spots. So any observations you can upload to AAVSO will automatically become part of the set. And anyone who uses your analysis in a study must then... Oh, is the rocket launching? I hear someone speaking. Oh, okay. So any observations you upload will automatically become part of the set. And if your analysis gets used in a study, then they must invite you to be a co-author on the paper. So when you upload to AAVSO, it's listed under your observer code rather than your name for privacy reasons. But if you want to collaborate with another observer, there's like a collaborate button on the website that sends a request to AAVSO. And this happened to one of my students, Alex. A while ago, Alex received an email from AAVSO asking if he'd like to collaborate on a study that was using data from a transit he had analyzed and uploaded of WASP 77AB. It had an attachment from a student at Arizona State University, Fred Nuger. Alex said he was interested, and after that, it was only several months until publication, but he got regular updates as to what was going on with the project. He had an opportunity to review the paper and offer any feedback on the draft. Needless to say, he was thrilled. He was a high school student, right? He had fortuitous co-authorship on a paper that got published in an academic journal. So one of the many things that I love about Exoplanet Watch is this culture that they've cultivated of sharing credit with everyone who contributes, and that could be you. So I hope that some of you will consider joining this vibrant and active Slack channel of NASA Exoplanet Watchers. We're very easy to find. The group is very fun. There's a special beginners channel for people just getting started. There's a book club. There's Tuesday, the book club is a journal club now. There's Tuesday trivia and Wildlife Wednesdays, a very active astrophotography channel, and Rebecca Black memes every Friday. And when you ask questions on this group, people answer. And when you post your first light curve, you are guaranteed to get several celebration emojis and words of encouragement. It's welcoming and collaborative and supportive in exactly the way that I think science is supposed to be, but often isn't these days. And as a teacher, I feel really good about sending my students there to ask questions and engage with astronomers who are much more experienced and knowledgeable than I am. So as we've said, all the planets we can image from the ground are hot Jupiters, gas giants that are close to their host stars. These are not rocky Earth-like worlds. So, why do we care about them so much? Why do we need a citizen science project of such enormous proportions to study worlds that are too extreme for life as we know it anyway? Well, first of all, we don't yet have the technology for rocky Earth-like worlds. Those are hard even for JWST. Our planet is too small relative to the sun. It blocks too little of its light. It orbits too infrequently. NASA's next flagship mission, the Nancy Grace Roman Space Telescope, which is going up in just a few months now, ahead of schedule, will pave the way for a possible mission even farther in the future, like Habitable Worlds Observatory, to image and characterize Earth-like worlds around sun-like stars. But the second thing is we have a lot to learn from hot Jupiters. We've said earlier that their very existence in this unexpected position close to their host star challenges our theories about how planets form in the first place. The chemistry of their atmospheres teaches us all sorts of things about planetary science, a few of which might be relevant to the future of our own planet. Hot Jupiter's orbital properties teach us about tidal forces and general relativity, and who knows, maybe the properties that make hot Jupiters too extreme for life as we know it actually might make them well suited to life as we don't know it. So, studying hot Jupiters will pave the way for our ability to find and study planets a little more like our own pale blue dot. Thank you. I'll end there. And I have Carl Sagan's pale blue dot video if anyone wants to watch it again in the presentation. Sometimes I end with that, but it looks, I'm guessing based on what has gone before, that all of you have seen that video many, many times.
Probably not everybody.
Well, I'm happy to play it. It's just a few minutes long and it's very inspirational. Here, I'll share again.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on the mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, In all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pink blue dot, the only home we've ever known.
This last bit here is from the opening of Cosmos, the movie.
I've heard that so many times, but it always gives me chills. Carl Sagan's narration is so timeless.
We ended up in the Eagle Nebula now. All right, any questions? Hard to follow that up, but
Yeah, it's hard to follow Carl Sagan, but certainly happy to take any questions and distribute the links to the Exoplanet Watch Slack channel and AAVSO and any other information that anyone might be curious about.
yeah, we can get that into our newsletter as well. Any questions?
I have a question. Can James Webb see any Jupiter-like worlds directly image big Jupiters? The direct image, do you know?
Were you able to hear that?
Was the question whether there have been any direct images of exoplanets?
Whether the JWST can image exoplanets directly, like Jupiter-sized ones.
I think that's a great question. I have seen I think JWST might have an occulter. I know that some instruments have a thing where like a star shade that you can occult the brightness of the star and then you can actually see planets going around the star. I think I'm not sure if JWST has one of those or not, but I know that I've seen those, and that's become more common in recent years, directly imaging exoplanets using all sorts of interesting techniques like interferometry, even from the ground, to see some of these things going around. But we haven't been able to do it for rocky Earth-like worlds. They're all ones that are much closer, but the coming mission should be able to have some of those capabilities. That's a great question. And just as another plug for the Exoplanet Watch Slack group, if you stick that question onto that group, you would get a lot of very knowledgeable answers that are more knowledgeable than I am about those missions.
Very cool. Can I ask who has reported, who has an observer code with the AAVSO? Other than Riyadh. I have one. The only observations I ever submitted were for Epsilon Origi, which is a really interesting occulting system that may be a planetary disk or who knows exactly what. but this talk has made me feel like I need to dust that off. So
It's so fun. And they welcome even visual observations. Like half the observations that people submit are visual. I have my students go out and look at Delta Sep. That's our class pet star. And it has a 5-day period of brightness changes. And even I'm not great at observing those brightness changes, but some people are, including some of my students, have been able to capture visual observations of this star brightening and dimming because it has a close by comparison star to it that is relatively stable. And so you can look at that from night to night. And it's just really neat to be able to see science happening. Like the sky is your laboratory. There's an AAVSO observer who wrote a book called The Sky is Your Laboratory. And it's really cool. It's really fun to get out there.
And I guess one other plug for visual variable star observing is just that oftentimes as astronomers we get asked at public events, well, what can you see happening live in space? And there's not a whole lot. You can see Jupiter rotate, you can see the shadows move across the shadows of the Terminator move across the surface of the moon. But beyond that, unless you get a close by comet or a close by asteroid, there's not a whole lot you can see move through a telescope. You can see the space station. Yeah, that's moving really fast. But like variable stars actually change in real time, and you can see Algol dip on a fairly frequent basis, a 3-day basis. So it's just cool to be able to see something with your own eyes that is physically happening out in space, like changing in real time.
Yeah, it's so cool. I feel like over the course of the semester, we kind of develop almost a relationship with Delta Sep and like sort of the stars we adopt in the class. And for exoplanet transits, like you can't really tell that the star's light is changing, but the exotic software actually does have a live mode where you can plot it. So you could sort of screen share and plot the light curve as the data come in, which is kind of fun.
I have a quick question. If somebody's using a monochrome camera, are there particular filter wavelengths that would help to do this kind of work?
That's a great question. A lot of the host stars tend to be redder. So a lot of people use red filters if they have them or infrared. But they'll take any wavelength. That's part of what you input into Exotic when you start running a transit is you would let it know either if you're using a standard filter, just the name of that filter, and they tell you what the letters are to specify what filter you have. Or if you're using a non-standard filter or an astrophotography filter, they'll ask you to at least approximate the passband of the filter and like just the full width at half max. And then you can because transits look different at different wavelengths, they are interested in all the colors. So there was one of the Pandora targets, WASP 69b, for example, that my students observed, and it's really bright. And we were using a robotic telescope, Las Cumbres, on which telescope time is limited. We only had 20 hours or something, but we got images in multiple filters. We just had it cycle through the filter wheel for the whole 4 hours because the exposure times were so short, and it was great for a lot of reasons. First of all, I felt like I was getting 4 transits for the price of one, where telescope time was concerned. And then also we could get a little bit of color information about the star, which was kind of cool. And it wasn't as conclusive as we hoped, because there's just so many other factors, as we all know, that interfere with observations. But it was like certainly added to the database several little pieces of information that could later be used to build a more complete picture of what the star was doing. So
yeah. Great. Thank you.
I have a question. Have amateurs done the kind of studies you're talking about? Do you know for a TRAPPIST-1, which has been really important because of the 7 rocky planets orbiting it?
Yeah, that's a great question. The students all want to do the TRAPPIST system, but those dips are too small for us to see with the telescopes to which we have access. You'd need a bigger telescope to be able to see dips that small. And I forget how big they are, but I've looked at them a number of times because so many students want to get them. And really for and I've had students even with as small as a 3-inch telescope contribute good transit observations, but those tend to be very bright stars with very deep dips. And the TRAPPIST, unfortunately, ones aren't quite bright enough with deep enough dips for us to get. So we're leaving those to the pros, but there are plenty of planets out there that have bright host stars with deep dips. So there's lots of potential targets even without TRAPPIST, but yeah, that would be super cool to be able to get that one.
Hello, I'm very new to uh astronomy, and it's really interesting. I saw in the news, I think it was a month ago, that um an asteroid hit the Midwest, and it made a huge thud. And I'm just wondering, like, what slows asteroids down, and like, what's the difference between a law and a theory?
Oh
Like a
God.
scientific law and a scientific theory.
These are
Also,
great
for
questions.
the the third question, if we can't see a planet and we want to contribute, can we do the math to figure out where this planet is, even though we can't see it?
Yes. Well, let's see. I'll start with the first one. So the first one is what slows asteroids down. Probably Earth's atmosphere is the most important factor in that. Certainly, there's a very active group studying asteroids called the Minor Planet Center that tracks all the known asteroids. And the latest telescope that just came online in Chile, Vera Rubin telescope, has discovered all sorts of additional bodies that are out there. Of course, the ones we all worry about are the ones that cross Earth's orbit, and to my knowledge, or that are potentially hazardous. To my knowledge, there aren't a lot of those. So we're lucky, but we don't always see them all, like that one that came down recently unexpectedly. So yeah, that would be definitely something interesting to study. And they study asteroids and light curves of asteroids to figure out what shapes they are and whatnot. So very, very active area of research that has some relation to exoplanets. But the main one that is related to exoplanets would be the second question about, if we can't see them, can we do math to contribute knowledge of their positions? To which the answer is certainly yes. You don't need to own a telescope to participate in NASA Exoplanet Watch. They have a data checkout system. Some of the targets, even for the data checkout system, I believe, are TESS objects of interest, for which they are sometimes planet candidates, not even planets. And then that's exactly what we do when we try to put in the priors for the orbital period and the semi-major axis and all the parameters of it. We take data that have been contributed previously about those planets to do some computations to figure out how to approximate the parameters of the planet so that we can figure out where it is. And so there are ways of doing that. Sometimes it's harder for planet candidates because of that, because for the confirmed ones, their knowledge about where the planet is and what its orbital period is and whatnot are already in the system. And then I forgot the third question. What was the third question again? Oh, law and theory, right? Haha, you're gonna have me put my science teacher hat on for that. In general, a law is taken to be an observation that like, I guess the best way is an example that the sun comes up every day is a scientific law, and then the explanation for that having to do with whatever model we're using to make predictions, that would be the theory. So the law is something like the sun coming up every day, and then the theory is why we think the sun comes up every day, if that is helpful. Great question.
Very
Thank
cool.
you.
All right, I think that's all the time for questions. It's not for presentations.
Thank you so much. It was so fun to be here.
Thank you, Kalée.
Thanks again. Diane, would you like to close the meeting?
Of course, yep. Guess you can turn the camera around.
It's official, scholarship has been scrubbed.
Yeah, the launch was scrubbed, so we didn't miss anything.
Oh, great. I mean, not great. That's too bad. But I was like wondering the whole time I was speaking, like, am I missing a lunch? Yeah.
All right, so thank you all for joining us tonight. And our next event is this upcoming Saturday, Stargate Open House. Our next meeting will be the first Monday. June. Yes, June 1st at Cranbrook. And right now, some of us are going to be heading over to Jimmy's Tavern at the back of the National Coney Island on Van Dyke Road, just north of 12 Mile, for a little after meeting get together. So
Yes.
gastronomy, we call it. So have fun and be safe, everybody. Good night.
Good night. Thank you.